Dear students, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. Myself, Jaimin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 2, which is Solution Thermodynamics. So in this lecture, we are going to discuss about the ideal gas mixture model, or can say that Lewis-Randall rule. Then we are going to discuss about the generalized Gibbs-Duhem equation and excess property. So let's discuss about the ideal gas mixture model or the Lewis-Randall rule. The calculation of fugacity of component in mixture is a not very easy task. In order to simplify evaluation of methodology, the mixture is modified as the ideal solution. As a devised model is known as the ideal solution model or Lewis-Randall rule. In this model, fugacity determined by the deviation of actual solution from ideal model behavior. Lewis-Randall rule is a simple equation and is therefore widely used for the calculation of fugacity in ideal solution. It allows the calculate fugacity from mixture without any information about the solution except its composition. Lewis-Randall rules are valid only for the when intermolecular force mixture are similar to those in pure state. So this model only used when intermolecular force in mixture are same as a pure state. So there will be no intermolecular force difference in pure state or in solution. So this is the first assumption for the Lewis-Randall rule. Second assumption, at low pressure when gas behave ideally. So it's only used for lower pressure. So we can apply this Lewis-Randall rule, or we can use the ideal gas model when pressure it's a lower and it's a gas or system behave like ideally. Okay. Then third observation that can be given by if physical property of solution are near about same. So physical property of solution is near about same as a pure state. So we can use the Lewis-Randall rule when the intermolecular force of mixture are similar to those in pure state at lower pressure when gas behave ideally, and physical property of solution are nearly same. The limitation of Lewis-Randall rule, or can say that this ideal gas model, is that at moderate pressure and at high pressure it will not give correct answer or not give correct result. So this is the limitation of the Lewis-Randall rule. Lewis-Randall rule states that the fugacity of each component in ideal solution is the product of mole fraction and fugacity of pure component at same temperature, pressure and composition. So Lewis-Randall rule states that the fugacity of each component in ideal solution is the product of mole fraction and fugacity of the pure component at same temperature, pressure and composition. To derive this equation, let's consider alpha is equal to V real minus V ideal. V real, which means volume of real gas and volume of ideal gas. So can say that alpha that can be given by V minus RT upon P. We know that for ideal gas, equation of state is a PV is equal to nRT. Okay, so this becomes our ideal V. So can say that V is equal to nRT upon P. For one component, this equation becomes RT upon P. So we can write V ideal is equal to RT upon P. For pure component, ln Fi upon P is equal to 1 upon RT integration of 0 to P Vi minus RT upon P into dP. This becomes our equation number 1. So this is for the pure component. Same way we can write for the mixture. How this equation come, we will discuss about this equation in method measurement of fugacity by different method in a furthermore lecture. So just remember this equation right now. We will discuss about how this equation come in next further lecture. Now if I want to write this equation for the solution, then what I have to change? I have to just make this fi instead of fi bar instead of this fi, and p instead of pi bar. So for the mixture, that equation becomes ln, there is a fi, so in solution there I have to write partial molar property, so it becomes fi bar upon pi bar is equal to 1 upon RT. R is a constant, that's why we cannot write R bar or T bar. Then volume V bar minus RT upon P at dp. So this becomes our equation number 2. By subtracting this equation number 1 and this equation number 2, we will get ln fi bar into p upon fi into pi bar is equal to, taking 1 upon RT common, so by integrating 0 to p, vi minus RTP minus vi bar plus RTP. So this RTP becomes cancelled because it makes minus minus plus, so we can write vi bar minus vi and taking the dp common. So this becomes our equation number 3. So since pi bar is equal to, we know that pi bar is given by yi into p. So we can easily simplify the equation in this form. So ln fi bar upon yi fi bar. So we are just taking fi bar is equal to yip. So pp cancel. So this equation becomes fi upon yi into fi bar is equal to 1 upon RT integration of 0 to p vi bar minus vi to dp. For ideal component, vi bar and vi both are same. Partial molar property and molar property for the particular component will be a same. So this difference becomes 0, and 0 multiply with anything becomes 0. So this equation becomes ln fi bar upon yi fi is equal to 0. Now if I am going to remove this ln, then I have to take exponential this to 0 both. So we will get the fi bar upon yi fi is equal to exponential power of 0. Power of 0 in anything it becomes 1. So this becomes 1. So can write that fi bar is equal to yi fi. So this is our ideal gas model, or can say that Lewis-Randall rule that state that the fugacity in a solution, or can say that fugacity of each component in ideal solution is the product of mole fraction. So this is a mole fraction. So product of mole fraction and fugacity of pure component at same temperature and pressure. So fugacity in solution, or can say that ideal solution, that can be given by mole fraction of that particular component multiplied by fugacity of that particular component in their pure state. So this is about the Lewis-Randall rule. Now let's discuss about the Gibbs-Duhem equation. In mixture, the partial molar properties of components are related to one another by one of the most useful equations, which known as the Gibbs-Duhem equation. It tells us how the partial molar property change with composition at constant temperature and pressure. The various forms of Gibbs-Duhem equation are related thermodynamic relation that are valid for condition of constant temperature and constant pressure. This equation tells us partial molar property of mixture cannot be changed independently in binary mixture. If the property or molar property of component increase, the partial molar property of other component should be a decrease. Gibbs-Duhem equation find the wide application in solution thermodynamics and in chemical engineering that include in absence of complete experimental data, in absence of complete experimental data, Gibbs-Duhem equation used for the calculation of additional property. For example, experimental data are available for activity coefficient of component 1. Then using this data we can relate the or we can find activity coefficient of other component over same constituent range or concentration range for the estimation using the Gibbs-Duhem equation. Similarly, thermodynamic consistency of experimental data can be tested using the Gibbs-Duhem equation. So we can check the data is correct or not. So thermodynamic consistency test is valid or not, or we can for the thermodynamic consistency test Gibbs-Duhem equation is a use. For example, if data of partial molar property of each component measured in experiment, then that data is right or correct or not, that can be checked using the thermodynamic consistency test using the Gibbs-Duhem equation. Using the Gibbs-Duhem equation, we can calculate partial pressure from isothermal total pressure data. Using Gibbs-Duhem equation, we can also calculate partial pressure data and obtain from the isobaric boiling point data. Using Gibbs-Duhem equation, the isobaric Tx data easily convert into the xy data using this Gibbs-Duhem equation. For partial molar property, we know that Mt is equal to summation of Ni into Mi bar. So this becomes our equation number 1. At constant temperature and pressure, this equation becomes Mt is equal to summation of Ni dmi bar plus summation of Mi bar into dni. So this becomes our equation number 2. At constant temperature and pressure, dmi bar is equal to 0. So this equation becomes dmt is equal to summation of mi bar into dni. This equation becomes 0 for the constant temperature and constant pressure. So can say that summation of ni dmi bar is equal to 0, which becomes our equation number 4, and this becomes our equation number 3, and this becomes our equation number 4. This is a general form of Gibbs-Duhem equation. So this is general form of Gibbs-Duhem equation. If we are going to replace this m with the chemical potential, then that can be given by Ni is equal to d mu I is equal to 0, or can say that this m is replaced by the Gibbs free energy. So if we are going to replace this m with Gibbs free energy, this term becomes like d of g bar, and we know that g bar, which is a partial molar Gibbs free energy, which known as the chemical potential. So this equation becomes like summation of Ni du mu I 0. So if we are going to divide this Ni with total number of moles, then this equation becomes summation of xi d mu I is equal to 0. Mole of particular component upon total mole, which gives mole fraction. So this Ni is replaced by the xi. Xi is a mole fraction of particular component I. Now let's derive the other form of Gibbs-Duhem equation using this equation. Let's take this equation number 6 and this is our equation number 5. So using this equation number 6, we can derive the various form of Gibbs-Duhem equation for binary mixture. Equation number 6, that can be given by x1 d mu 1 plus x2 d mu 2 is equal to 0. So x1 d mu 1 is equal to minus x2 d mu 2. Now dividing by the dx1, so if we are going to dividing above equation with x1, then this equation dividing by dx1, not only x1, so this equation becomes x1 is equal to d mu 1 upon dx1 is equal to minus x2 into del mu 2 upon del x1. Here temperature and pressure is a constant, so we have to write partial derivation. So this d becomes partial d, or can say that del. Okay, so x1 into del mu 1 upon del x1 is equal to minus x2 into del mu 2 upon del x2. But we know that x1 plus x2 is equal to 1. So x1, which becomes 1 minus x2. So if we are going to differentiate, so this becomes dx1 is equal to minus dx2, or can say that del x1 is equal to minus del x2. So replacing with this term, or can say that replacing del x1 instead of minus del x2, this equation becomes this minus del x1, we are going to replace with minus del x2. So this equation becomes like x1, which is as it is, del mu 1 upon del x1. So del mu 1 upon del x1 is equal to minus x2 into del mu 2 upon x1. Okay, so if we are going to replacing this del x1 with minus del x2, then this minus minus becomes plus. So here just becomes x2 upon del mu 2 upon del x2. So this is how we can get the data from the component 1, or from component 1 of we can find the data of chemical potential from component 1 to from component 2. So this is a Gibbs-Duhem equation in term of the chemical potential. So this is a Gibbs-Duhem equation in term of chemical potential. Now let's take this is our equation number 9. Introduce the chemical potential in term of the fugacity, then that can be given by x1 is equal to del f1 bar upon del x1 is equal to x2 into del f2 bar upon del x2. So this is a Gibbs-Duhem equation in term of fugacity. So partial mole of Gibbs free energy G bar is equal to mu, and we know that G bar and mu is equal to RT ln Fi bar. So RT ln will be cancelled from both sides. So this equation becomes del F1 bar is equal to del F2 bar. So this is a Gibbs-Duhem equation in a fugacity term. Now let's write Gibbs-Duhem equation in term of activity. What is meaning of activity? We will understand the meaning of activity in further lecture, but let's understand little bit about the activity. Activity, which meaning of activity, which means fugacity in solution upon fugacity at standard state for that particular component. So this is about the activity. We will discuss about more detail in activity in a further more lecture. So if we are going to replace this fugacity in term of the activity, then this equation becomes del EI Fi bar upon del x1 is equal to x2 into del f2. So this is not bar, this is a f naught. So if we are going to replacing this Fi bar, it becomes Ai upon Fi naught. So f1 bar becomes A1 into A1 f naught. Similarly, f2 naught into A2 upon del x2. So this is the fugacity for in term of the activity. Now for the standard state fugacity will be cancelled for the same for both components. So this equation becomes like x1 del a1 upon del x1 is equal to x2 del a2 upon del x2. So this is the fugacity in term of activity. Now if I want to write the in term of the activity coefficient, then it becomes x1 del ln gamma 1 upon del x1 is equal to x2 into del ln gamma 2 upon del x2. So this is a Gibbs-Duhem equation in term of the activity coefficient. So we understand the various form of Gibbs-Duhem equation in this lecture. Now let's discuss about the excess property. What is meaning of excess property? Excess property, which means real property minus ideal property. So can say that the difference between real property and property of real solution of that ideal solution is known as the excess property. So equation for the excess property that can be given by ME is equal to M minus M ideal. So ME is the excess property, M which is a real property, and MID is the ideal property. So we can write that equation in terms of the change in property. So it becomes like this: delta M minus delta M of ideal. So this is all about the excess property, and this is all about today's lecture. I am completing my lecture here. Thank you.